Okay, good morning. In today's session, I will be discussing about the shear stress distribution in beams. Actually, in beams, the shear force will be acting at all the sections. Shear force on the cross sections, that is the tangential sections. Because of the transverse load, every cross section is subjected to shear force in combination with the bending moment also. Okay, the effect of this shear stress as compared to bending stress will be negligible, and hence it is generally neglected. But sometimes it will be required to consider the shear stress distribution across the beam cross section. Now we will be deriving an expression for the shear stress distribution across beam section. For that, we consider a small portion of the beam as shown in the figure ABCD of length dx, small length of beam dx between two cross sections AB and CD. We consider this and we'll see the shear stress at a distance tau, at a distance y from the neutral axis. We'll derive an expression for the shear stress at a distance y from the neutral axis. Okay, as shown here, the shear stress at a distance y from neutral axis. That means at the level of EF. Okay, so for that, consider a small elemental cylinder along the length between these cross sections AB and CD. Small elemental cylinder of area dA. In the shaded area EFGH. In the shaded portion, we consider a small elementary cylinder of area dA. Okay, and we are considering here a beam subjected to UDLC. Okay, so because of that, you will have shear force and bending moment changing from one cross section to the other cross section. Okay, and let the shear force and bending moment at cross section AB be M and F say, and shear force and bending moment at CD be M plus DM and F plus DF say. Okay, so because of this, bending stresses will be developed on these two cross sections. Okay, and the bending stress distribution is linear, as we know. Okay, so at a distance that means on the elementary cylinder, let sigma be the stress acting on end AB. Okay, and sigma plus delta sigma be the bending stress on the face CD, on the end of the cylinder lying on the face CD. Okay, that means at the left end of elementary cylinder, the bending stress is sigma, and the bending stress on the right end of the cylinder, elementary cylinder, is sigma plus d sigma, say. Okay. So here m is the bending moment at AB, and m plus dm is bending moment at CD. F is shear force at AB, and F plus dF is shear force at CD. Okay. And here we are calling it as actually F. Okay. F is the bending stress at left end. F plus dF is bending stress at the right end. Okay. And dA is area of elementary cylinder. Okay. Elementary cylinder. So as per the bending equation, we know the relation m by I equal to F by Y, where m is the bending moment, I is the moment of inertia, F is bending stress, and Y is the distance at which we are considering the bending stress from the neutral axis. Okay. From this, you will get the equation for bending stress as m by I into Y. Okay, where Y is the distance here of elementary cylinder. Okay. Similarly, this is at the left end of the elementary cylinder, and at the right end, the shear stress, the bending stress is F plus dF. So bending moment is m plus dF. So again, from bending equation, we will have the relation as F plus dF equal to m plus dm by I into Y. Okay, from which yeah, actually the force now, the force will be F into d. On the elementary cylinder, the force due to bending stress is F into dA, and we know F is equal to m by I into Y. Okay, that is the force acting on the elementary cylinder at the left end is m by I into Y into dA. dA is area of elementary cylinder. Similarly, the force acting at the right end of the elementary cylinder is the stress multiplied by area again. Stress is F plus dF into dA. Okay. So here F plus dF is from bending equation m plus dm by I into Y. Okay. Multiplied by area dA gives the force acting on the elementary cylinder. So from left side you have the force m by I into Y into dA, and from the right you have m plus dm by I into Y dA. Okay, that means there will be some unbalanced force acting on the elementary cylinder. Okay, so that unbalanced force is given as the difference of these two forces. Okay, unbalanced force due to changing bending moment is given as the difference of these two forces, m plus dm by I into Y dA minus m by I into Y dA. Okay, so this comes out to be dm by I into Y dA. Okay, so this is the unbalanced force on one of the elementary cylinder in the shaded area. Okay, which lying about distance Y, lying about distance Y. So we are considering the shear. We are finding out the expression for shear stress at the level EF at a distance Y from neutral axis. For that, we need to consider all the unbalanced force acting on this shaded area. Okay, from left and right, we will have two forces. So the unbalanced force acting above the level at a distance Y, above the level of EF. Okay, the total unbalanced force is given as the sum of all the forces acting on elementary cylinders. Okay, so the elementary cylinder, the unbalanced force on one of the elementary cylinders is given by this. So the total unbalanced force is obtained as the summation of all such elementary uh, forces acting on elementary cylinders. Okay, summation is nothing but integration. So the total unbalanced force is given as the integral of dm by I into yda. So taking dm by I out, we will have integral yda, which is nothing but moment of area about neutral axis. Moment of shaded area about neutral axis. Okay. So this is the total unbalanced force acting on the shaded area above distance y from neutral axis. Above distance y from neutral axis. Okay. So this force causes shear failure if not resisted. This force causes the failure along the face EF. Okay. If the shear resistance is less than the force. Okay. If the shear resistance offered at this phase, at this level, is not enough, then the failure takes place as shown here. Okay. So assuming that the shear resistance is equal to the unbalanced force. Okay. So the shear force, let tau be the shear force now at this interface. If tau is the shear force, then the shear resistance offered by this cross section, by this section at level EF, which is of area B into dx, B into dx. Okay, the area on which this shear stress tau acting is B dx. So the shear resistance is tau into B dx. Okay, and this is equated to the unbalanced force above the level here. Okay, understand? So wherever you consider the shear stress, then you need to consider the unbalanced force acting above that level. Okay, acting on the cross section above the level under consideration. Okay, above the distance y under consideration from the neutral axis. Okay, so here the shear resistance must be equal to this unbalanced force. So we equate now the shear resistance to unbalanced force. Okay, so the shear resistance is given by this. By equating these two now, you will have tau equal to dm by I into ay by b dx. Okay, b dx we are taking to the right hand side. So from this rearranging these terms, dm by dx into ay by ib, ay by ib, and dm by dx is nothing but the shear force. Dm by dx is nothing but the shear force. So the shear stress at a distance y from neutral axis is given by this expression, where F is the shear stress and A is area above distance y, and y bar is distance of CG of this area from neutral axis, and I is moment of inertia of the entire section, and B is width at distance y from neutral axis. Okay, so in case of rectangular section, width is same throughout, from top to bottom, the width is same. Okay. So at all the distances, you will have the constant width for rectangular sections. Okay. Sometimes you may have circular section. In that case, width is not same. Width is not same. Okay. So width will be variable with distance y. Okay. Width varies from neutral axis. As the distance from neutral axis changes, width also changes. In case of trapezoidal sections also. In case of trapezoidal sections, you will have the changing width from neutral axis. Okay. So this expression gives the variation of shear stress now from neutral axis across the section, across the cross section. The shear stress at any distance from neutral axis is given by this equation. Okay. Using this now, we can find the shear stress variation from top to bottom of the cross section. For any given cross section, we can find the shear stress distribution. Okay, from top to bottom. Okay. Now let us consider one example. Example of a rectangular section. Say a rectangular section of width 100 mm and depth 250 mm. Say depth 250 mm. Okay. Now to find the shear stress distribution. Okay. Yeah. Let us consider again distance y. Okay. And this distance is d by 2. General case we can first consider. After that, we substitute the values. Okay. Here d is equal to 250 and b is equal to 100. Okay. First, let us consider the case of general section of width b and depth d. Okay. Now the distance of centroid and the area of this is A. Okay. So the area A is equal to, so this depth of this section, depth of the shaded portion is d by 2 minus y. Okay. And y bar is equal to y plus half of the depth. That is half into d by 2 minus y. Okay. So A is equal to now b into d by 2 minus y, and y bar is equal to y plus half d by 2 minus y. So which will be half into d by 2 plus y. Okay. Taking y inside, we will have half into d by 2 plus y. This is y bar. Okay. So now let I be the moment of inertia. For rectangular section, moment of inertia is BD cube by 12 about neutral axis, centroidal axis. So let F be the shear force. Let F be the shear force. Now we see the equation for shear stress, tau. What is tau here? Tau is equal to F A y bar by IB. Okay. So just now we have seen the values of A. A is b into d by 2 minus y, and y bar is half into d by 2 plus y by moment of inertia, let it be I only, keep I, into width. Width is constant. Actually, b is here, the width at distance y. In this particular case of rectangular section, b is same from top to bottom. Okay, so b is constant here. So this reduces to now f by ib. Here b cancels. F by 2i. Okay, f by 2i into d square by 4 minus y square. That is d by 2 minus y and d by 2 plus y. Okay, so this is the equation for shear stress at any distance y in case of a rectangular section. Okay, so now giving different values to y, you will get the shear stress distribution across the rectangular section. Okay, for example, giving a value of 0, now tau is equal to f by 2i into d square by 4 minus y square, d square by 4 minus y square. Okay, so at y is equal to 0 means at neutral axis. Actually, y0 means at neutral axis. Y is the distance from neutral axis. So the shear stress will be maximum at y is equal to 0, because from this equation it is clear that is for minimum value of y you will have maximum value of tau. The minimum value of y is 0, so the maximum shear stress across the section is at y equal to 0. So at y equal to 0 you will have f by 2i into d square by 4, or replacing now I by bd cube by 12, you will have f by 2 bd cube by 12, f by 2 bd cube by 12 into d square by 4. So by simplifying this, you will have 6 by 4 into f by bd, or 3 by 2 into f by bd. This is tau maximum. Okay, and actually average shear stress across the section, average shear stress when shear force is F is given as F by BD. The average shear stress across the section is given as F by BD, where F is the shear force. Okay, so now the maximum shear stress in case of rectangular section is 3 by 2 times the average shear stress. F by BD is nothing but average shear stress. So tau maximum is equal to 1.5 times average shear stress, tau average. Okay, so this is the relation between average and maximum shear stresses in rectangular section. Okay, so if you draw this distribution now, the maximum shear stress is 3 by 2 into f by b. Now at x equal to at y equal to d by 2, from this equation, at y0 you will have maximum shear stress. Now at y equal to d by 2, at y equal to d by 2, you will have zero shear stress. Okay, tau is equal to 0. At y is equal to plus d by 2 or minus d by 2. That means at the bottom end or top end. Okay, and how about the variation of the shear stress? It is parabolic. Okay, the variation of shear stress is parabolic. Variation of shear stress is parabolic. Okay, So here the shear stress is maximum, and at the top end and bottom end you will have zero shear stress. Okay, and this is the equation for parabola here. Okay, because shear stress varies as a square of distance from neutral axis. Okay, so this is the shear stress distribution for a rectangular cross section. Okay, for a rectangular section, the shear stress distribution is given as given by this diagram. Okay, zero at top and bottom ends, and maximum at neutral axis, and maximum shear stress being equal to 3 by 2 F by BD. 3 by 2 F by BD. Okay. Now this is general case. Okay. Now we can substitute the values. If the Let us consider some numerical values. Let the shear force at the section is some 20 kilonewtons. Okay, in a rectangular beam, the shear force, maximum shear force is 20 kilonewtons, and width is 100 mm, depth is 250 mm. In this case, find the distribution of stresses across the section. Okay, so maximum shear force is 20 kilonewtons. Okay, just now we have seen what is the distribution here: 0 at top and bottom, and maximum at neutral axis. Okay, and what is that maximum shear stress? 3 by 2 into F by B. So here F is 20 kilonewton, that is 20,000 into 100 divided by 100 into 250 area. Okay, so this gives the shear stress. Okay, 4 by 5, 1.2 Newton per mm square. It comes out to be 1.2 Newton per mm square. Okay, and the average shear stress is F by BD. Average shear stress is F by BD, which is 20,000 by 100 into 250. That is 0.8 Newton per mm square. Okay, understand? And shear stress at top and bottom ends will be. Let us consider another example. The shear stress, maximum shear stress not to exceed 2 Newton per mm square, and the shear force is 25 kilonewtons. Shear force is 25 kilonewtons, and depth of beam is 2 times the width of the beam. In that case, you find the cross section dimensions so that the shear stress not to exceed 2 Newton per mm square. 2 Newton per mm square. Okay. So this is another example. So how will you get now? This is maximum shear stress. And what is the maximum shear stress across the beam section in case of rectangle? It is 3 by 2 into F by BD. And you replace D by 2B. Okay. So 3 by 2 into F by B into 2B. Okay. That is 3 by 4 into F by B square. So from this, B square is equal to 3 by 4 into F by tau maximum. Now substitute the values here. F is 25 kilonewtons and uh, tau maximum is 2 Newton per mm square. Okay, yeah, from this you will get the width of beam section and depth is 2 times of this width. Okay, and that's how we find out the cross sectional dimensions when the allowable stress is given and the shear force are given. Okay, yeah. With this I conclude this session. Let us have one more session.
Like, share, and subscribe. Hit the bell icon for more updates.